Hello viewers, in this video I would like to discuss finite differences and Newton's forward and backward interpolation formula. Finite differences, here we have n plus 1 data points and we can write them as fx or xy pairs. Y is equal to fx, x is independent variable, y is dependent variable, and the values of x being equally spaced, xi is equal to x0 plus ih. I may take values from 0, 1, 2 up to n. Now we see first order differences, how we can write them. So delta fxi, delta is forward delta here, so fxi plus h minus fxi, and in short form we can write down delta fi is equal to fi plus 1 minus fi. I may take values 0, 1, 2 up to n minus 1. Now second order differences can be denoted as delta square fi, and these are the differences of first order differences. So delta square fi is equal to del fi plus 1 minus del fi. Now nth order differences are defined as del to the power n fi is equal to del to the power n minus 1 fi plus 1 minus del to the power n minus 1 fi. Let's see forward difference table. Here we have taken x in first column and it takes values x0, x1, x2, x3, x4. There may be many data points, but here we have taken only 5 data points, which are from x0 to x4, and corresponding value of fx is given in second column. So corresponding to x0 function value is f0. We may write it as y also. Y is equal to fx, so this will be y0. x1 is having corresponding value f1, it may be y1, and so on. So x4 may have corresponding function value as f4, which may be written as y4 also. So first order difference is denoted by delta f. So delta f0, delta f1, delta f2, delta f3. So what is the meaning of del f0? That is f1 minus f0. Del f1 is f2 minus f1. Del f2 is f3 minus f2. Del f3 is f4 minus f3. Now we come to second order differences. Del square f0, it is del f1 minus del f0. Del square f1 is del f2 minus del f1. Del square f2 is del f3 minus del f2, and so on. So we can calculate the differences, and because there are 5 points, so we will have differences up to fourth order. And general formula is del n fi is equal to del to the power n minus 1 fi plus 1 minus del to the power n minus 1 fi. Now backward difference is defined as del fxi is equal to fx minus fxi minus h. Here we have taken backward delta and this is the difference. So nth difference backward is del n fi is equal to del n minus 1 fi minus del to the power n minus 1 fi minus 1. We can write down it in tabular form also. First column is showing the x values x0, x1, x2, x3, x4, and second column is showing fx values f0 to f4. We can write down here y also, so y0, y1 up to y4. Now backward delta, that is first backward difference, is in third column. So del f is equal to del f1, del f2. So del f1 is equal to f1 minus f0. Del f2 is f2 minus f1. Del f3 is f3 minus f2. Del f4 is f4 minus f3. Basically numerical values of forward difference table and backward difference table are same, but here suppose let's take the first order difference, that is backward delta f1. This will be equal to forward del f0. So both of them are same in numerical value, notation is different. Now let's see a few observations. F1 minus f0 is equal to del f0, that is forward difference, is equal to backward delta f1, that is backward difference, is equal to delta f half, that is central difference. You can see that numerical value is same for all the three, forward, backward and central differences, but the suffixes are different, 0, 1 and half. We are not discussing here central differences as it is not given in UPSC syllabus. Now let's see the average operator, which is mu. So mu fi is equal to half fi plus half plus fi minus half. Now we can see shift operator, which can be denoted by e. So e fxi is equal to fxi plus h, and nth order is e to the power n, fi is equal to fi plus n. Now relationship between delta and e, we can write down del f0 is equal to f1 minus f0, which we have seen just now, is equal to e f0. So f1 is equal to e f0 minus f0. Now we take f0 as common, so e minus 1. So in short form we can write down del is equal to e minus 1, or e is equal to 1 plus delta, that is forward difference delta. Now we see one example based on this, that we have to show that del cube f0 is equal to f3 minus 3f2 plus 3f1 minus f0. We take first term on left hand side, that is del cube f0 is equal to, we substitute value of del, that is e minus 1 cube f0. We open this cube e minus 1 cube and apply each operator on f0. So e cube f0, 3 square f0 plus 3f0, 3e f0 minus 1, and then we see this is the result which we had to show. Now let's see Newton's divided differences in terms of forward differences. This is the formula, Pnx is equal to fx0 plus fx0 x1. Here fx0 x1 is divided difference, and into x minus x0 plus fx0 x1 x2, this is also divided difference, into x minus x0 x minus x1 and so on. So let's take divided difference of 2 points, that is fx0 x1, which is equal to f1 minus f0 upon x1 minus x0, x1 minus x0, because this is equally spaced, so value is h, 1 upon h, and f1 minus f0 is forward difference, so delta f0. Now we take 3 points, fx0 x1 x2. So in divided differences we can write down fx1 x2, the last 2 points we have taken, minus fx0 x1, the first 2 points, upon x2 minus x0, the last minus initial point. And in forward differences it can be written as, the first term fx1 x2 is 1 upon h delta f1, and the second term fx0 x1 is 1 upon h del f0, which we have shown in the previous step, upon 2h, because equally spaced, so x2 minus x0 is 2h. Now we simplify it and get 1 upon factorial 2h square del square f0. So in general, if we take n plus 1 points, so fx0 x1 up to xn, it is 1 upon factorial n h to the power n del n f0. Now we have this formula which we have written in previous slide. So we substitute values of fx0 x1, fx0 x1 x2 and fx0 x1 up to xn in this formula and get this expression, which is equal to f0 plus x minus x0 was there, and value of fx0 x1 is del f0 upon h, plus x minus x0 into x minus x1 were there, and the value of fx0 x1 x2 is del square f0 upon factorial 2h square, and the last term is x minus x0 x minus x1 up to x minus xn minus 1 into value of fx0 x1 up to xn, which comes del to the power n f0 upon factorial n h to the power n. So we got this formula, which is called Grigori-Newton forward difference interpolating polynomial or formula. Now we take x minus x0 upon h as p, and we substitute this value in the above formula. So we get Pnx is equal to f0 plus p del f0 plus p into p minus 1 upon factorial 2 del square f0 plus last term is p into p minus 1, p minus 2 up to p minus n minus 1 upon factorial n del n f0. Now let's see backward difference interpolating polynomial or formula, and this is the expression Pnx is equal to a0 plus a1 into x minus xn plus a2 into x minus xn into x minus xn minus 1 up to the last term, nth term is an into x minus xn into x minus xn minus 1 up to x minus x1. Now let's substitute x is equal to xn. So our expression becomes Pn xn is equal to a0, and if we see the second term, this becomes 0 and next also, so all the terms becomes 0 except the first term, that is a0, which we may write as fn. Now we substitute x is equal to xn minus 1, so our expression becomes Pn xn minus 1 is equal to fn minus 1 is equal to a0 plus a1 xn minus 1 minus xn. Here if you see, the first two terms will be non-zero and second term is first and second, these two terms are non-zero. Third and onwards all the terms are 0. So we have taken here two terms, a0 plus a1 xn minus 1 minus xn, which is equal to fn minus 1. Now we can find out value of a1 from here, which is equal to fn minus 1 minus fn upon xn minus 1 minus xn, which is equal to, this is backward difference fn upon h. And now we can substitute x is equal to xn minus 2, and our expression is Pn xn minus 2. Now we will have first three terms and rest of the terms will be 0, which we can write as fn minus 2, and from here we will calculate a2. a1 we got in the previous expression. We substitute values of a0 and a1 from the previous steps and find out values of a2, which is equal to del square, that is backward del square fn upon 2h square. So an we can find out, that is del to the power n fn upon factorial n h to the power n. Now we substitute all values of a0, a1 up to an in this expression, which was the initial expression, and write down value of Pnx. So we see that this formula is called Grigori-Newton backward difference interpolating polynomial. And now we put p is equal to x minus xn upon h, and we see that the formula can be rewritten in this form, which can be used to solve the examples. Here we take one example. The following data are taken from the steam table. Temperature in degree centigrades denoted by T, 140, 150, 160, 170 and 180, and pressure kilogram force per centimeter square denoted by P, and value for 140 is 3.685, for 150 4.854 and so on, and for 180 it is 10.225. Construct the finite difference table and hence find the pressure at temperature T is equal to 142 degree and T is equal to 175 degree. Here we see that 142 lies near 140, that is initial value, so we will be using forward difference table and forward difference interpolating formula, and 170 lies near to 180, that is the last point of the data lying between 170 and 180. So we will be using backward difference interpolating formula to calculate pressure at T is equal to 175 degree. Now we take first column as T and write down values 140, 150, 160, 170, 180. Corresponding value of P is 3.685, then 4.854 and so on. We can think of that T is corresponding to x and P is corresponding to fx, or in other terms we can say it is y. So we now find out first order differences denoted by del P. So first value under del P is 4.854 minus 3.685, which is equal to 1.169. Second value comes from 6.302 minus 4.854. Third value is 8.076 minus 6.302. Then last is 10.225 minus 8.076. So we got the first order differences in third column. Now we calculate second order differences in fourth column, which can be obtained from the differences, first order differences of first order differences. Similarly, third order differences del cube P can be obtained with the help of second order differences, and then fourth order difference is 0.002. There are 5 points, so we reach to only fourth order differences. Now we take P is equal to T minus T0 upon H. T is 142, that is we have to calculate pressure at 142, minus T0 is 140 upon H, difference between two consecutive values of T, which is equal to 10, and we get P value 0.2. Now we substitute this value of P in the forward interpolating polynomial. So this is the formula which we have derived in the previous tables. Here F0 corresponds to pressure, and P, small p, we have calculated, which comes 0.2 in the previous slide. Del F0 is first order difference, del square F0 is second order difference, and so on. So we substitute the values here and we get this expression. So P0 is 3.685. If we see the finite difference table, the top diagonal values we are taking. So next is 0.2, that is P del F0 is 1.169, then P into P minus 1 upon factorial 2, then second order difference first value. So we are taking all the first values in the differences, so 0.279 and so on. We calculate this value, which comes 3.898. Now we calculate backward difference formula. So for that also we need to have P value, and for backward difference interpolating formula we have given the value 175. So this value have been given to us, 175 minus 180 upon 10, which comes minus 0.5. So we use now backward difference interpolating formula and we substitute values here. F again represents here pressure, and small p, which we have got now, that is minus 0.5. So now we will be using the last column diagonal of finite difference table. So last differences of the table. So Fn is Pn, that is 10.225. Then P value is minus 0.5 into del Fn is the last value in the first order difference, plus P into P plus 1, that is minus 0.5 into 0.5 upon factorial 2, that is 2. Del square Fn is the last value in the second order difference, that is 0.375, and similarly we write all these values and calculate and get the value 9.100. Hello viewers, in this video I would like to discuss interpolation, approximation and Lagrange's interpolation formula. What is an interpolation? Basically, if we have n number of points, say x, y, y is a function of x. So if we want to find out value of y at a particular value of x, which lies between this set of data which is given to us, then we call it interpolation. So we are finding value of y at a particular value of x which is not available in the given data. So interpolation is a technique of estimating the value of a function for any intermediate values of independent variable x. So value of function means y or fx. Given a table of discrete data points xi, fi, it means we have x as independent variable, y or fx is dependent variable, and we are trying to find out value of function f at a particular value of x which is lying between these data points. So what is use of interpolation? Reconstructing the function fx. So either we can directly find the value of f, or we can reconstruct the function fx in terms of x when it is not known explicitly, and only the values of fx and or its certain derivatives at a set of points are known. So we can reconstruct the function and find out the value of fx by putting the value of x in that function. Replace the function fx by an interpolating polynomial px so that operations such as determination of roots, differentiation and integration for the function fx may be performed using px. So all these things we need to find out when we don't have exact solution, exact differentiation or integration. So we can use this numerical technique for doing that. Now interpolating polynomial, let's have xi fi points, I takes value 0, 1 up to n, be a given set of n plus 1 points, 0, 1, 2, 3 and so on up to n means n plus 1 points, where xi are all distinct. Then the polynomial px of degree less than equal to n is said to be interpolating polynomial if pxi is equal to fi, I takes values 0, 1 up to n. Why do we need interpolating polynomial? Basically we can find out or interpolate value of y for a particular value of x with the help of formula, but sometimes we need to have interpolating polynomial in terms of x. So for any particular value of x we can find out value of y with the help of polynomial. So Lagrange interpolating polynomial. The Lagrange interpolating polynomial exhibit the existence of polynomial for interpolation with unevenly spaced data. So we can have two types of data. Evenly spaced means difference between two consecutive values of x is same, and unevenly spaced data when difference between two consecutive values of x is different. So Lagrange interpolating polynomial, and we apply Newton's divided interpolating polynomial also, but here we are talking about Lagrange interpolating polynomial only. So we are taking values of y or f in terms of f0, f1 up to fn. Corresponding values are x0, x1 up to xn, and these are distinct point, and we say that polynomial can be depicted by pxi is equal to fi, and this is the function which takes n plus 1 values. So px can be represented as polynomial of nth degree in x. So let this polynomial be of the form, we take any form which we are writing here, and this form we will be finally finding out the exact form of this. So it is px is equal to a0 x minus x1 into x minus x2 up to x minus xn plus a1 x minus x0 x minus x2. See here x1 is not there. In the previous term x minus x0 was not there, up to x minus xn plus an, here x minus x0 x minus x1 up to x minus xn minus 1, here x minus xn is not there. Now we put x is equal to x0 in px. So our first term is here, all other terms becomes 0 because all other terms have x minus x0 term that becomes 0, so they become 0. So finally px0 is equal to f0, which is equal to the first term of the polynomial, which is a0 x0 minus x1 x0 minus x2 up to x0 minus xn. Now we find out a0 from here. a0 is equal to f0 upon this one. Now we calculate x is equal to x1 in the polynomial. We put this value and find out value of a1. So we got a1 this. Similarly we can put x is equal to x2 and we can find out value of a2, and finally we put x is equal to xn and find out value of an. All these values we can, substituting the values of a0, a1, an in the px, which is the polynomial we had assumed, we get the Lagrange interpolation formula, and this is the interpolation formula. Now we can write down it in a short form, where we can take coefficient of f0 as L0x and coefficient of f1 is L1x, coefficient of fn is lnx. So we have written it in short form, and further in summation form I is equal to 0 to n lix fi, where lix is this the product. So, and lixij is equal to 1 for I is equal to j and 0 for I is not equal to j. This formula can be used irrespective of whether the value x0, x1, xn are equally spaced or not, and formula is this same formula. The Lagrange polynomial passes through each of the points used in construction. For example, substitute x is equal to x1 in the Lagrange polynomial, all terms except the. Now let's so we have to calculate the value in terms of x. So if we simplify it, we will have a polynomial in x. It can be further simplified, and in the question we have to find out value of e to the power 1.5. So we put 1.5 in the above polynomial, that is x is equal to 1.5, and get this value 4.4301. Thank you. वेलकम टू द चैनल एंड थैंक यू फॉर वाचिंग द वीडियो. पिछले कुछ दिन वीडियो अपलोड नहीं हो पाया, अब मंडे टू सैटरडे डेली करेंगे. इस वीडियो में हम बात करेंगे एरर इन लैग्रेंजे फार्मूला. एरर इन लैग्रेंजे फार्मूला, अगर हमारे पास सीरीज में n डेटा पॉइंट्स हैं, के लिए हम फार्मूला लिख सकते हैं मॉड en इज लेस देन इक्वल टू मैक्सिमम ऑफ प्रोडक्ट ऑफ I इज इक्वल टू 0 n मॉड x माइनस xi upon n plus 1 factorial mn plus 1, where x belongs to x0, xn, and mn plus 1 is the n plus 1th derivative of the function, and maximum of it when x belongs to x0, xn. तो हमें फंक्शन का n plus 1th डेरिवेटिव निकालना. अब यही फार्मूले को, जो कि जनरल फार्मूला है, हम लीनियर इंटरपोलेशन मतलब दो पॉइंट्स के लिए देखते हैं कि जब दो पॉइंट्स हैं x0 एंड x1, इसका मतलब n इज इक्वल टू 1 और x लाई कर रहा है बीच में x0 एंड x1 के. सो वी कैन राइट डाउन mod even because n is equal to 1 is less than equal to n is 1, so n plus 1 factorial is 1 upon factorial 2, which is 1 upon 2. Maximum x0 is less than equal to x is less than equal to x1, and mod of, as it is given in the formula, product of x minus xi. So product of x minus x0, x minus x1, and mn plus 1, n is 1, so this is m2, और m2 क्या होगा, second derivative of the function, and mod of that and maximum x belongs to x0, x1. तो ये हमारा फॉर्मूला हो गया लीनियर इंटरपोलेशन. नाउ द मैक्सिमम वैल्यू ऑफ x माइनस x0 एंड मल्टीप्लाइड बाई x माइनस x1 जो है कहाँ आकर करेगी, इन दोनों के मिड पॉइंट. सो even mod is less than equal to 1 upon 8. 1 upon 8 क्यों, क्योंकि this is 1 upon 2 already here, and जब हम ये निकाल रहे हैं वैल्यू, x को वैल्यू रख रहे हैं x0 प्लस x1 अपॉन, एक बार फर्स्ट टर्म से 1 अपॉन 2 आ गया और दूसरी बार सेकेंड टर्म से 1 अपॉन 2 आ गया. तो दिस इज 1 अपॉन 8 x1 माइनस x0 होल स्क्वायर m2. जब आप यहाँ x की वैल्यू ये सब्स्टिट्यूट कर देंगे x0 प्लस x1 बाई, आपको ये फॉर्मूला मिल जाता है. So this is for linear interpolation. This is the error in Lagrange formula using the data sign point 1, which is given 0.09983, and sign point 2, which is also given 0.19867. Find an approximate value of sign 0.15 by Lagrange interpolation. तो जो डेटा है उसमें हमारे पास x0 गिवन है, x1, fx0, fx1 एंड x की वैल्यू गिवन है. सो ये सब फॉर्मूला हम इस पॉलिनोमियल में सब्स्टिट्यूट कर देते हैं and then we calculate, we get this value. So we know x is 0.15, x1 is 0.2, x0 is 0.1, x1 is 0.2 and f0 की वैल्यू 0.09983. सिमिलरली हम इस पोर्शन में भी वैल्यू रख देते हैं, ये 2 पॉइंट है डेटा में, तो आंसर आया x0 x1 तो n is 2. अब बाउंड कैलकुलेट करना है, लेस देन इक्वल टू 1/8 x1 minus x0 होल स्क्वायर m2. ये हमने अभी पिछली स्लाइड में देखा था जनरल फॉर्मूले में. पहले n के लिए जब n नंबर ऑफ पॉइंट्स थे और जब 2 पॉइंट्स हैं तब इवन हो जाता है. एंड m2 क्या होगा, सेकंड डेरिवेटिव ऑफ द फंक्शन, जहाँ की मैक्सिमम वैल्यू लेनी है इसकी एंड x लाइज बिटवीन x0 x1. सो हमें मैक्सिमम ऑफ f डबल डैश x मॉड ये कैलकुलेट करना है when x lies between this. So maximum of, पहले हम m2 निकालें, fx हमारे पास है sin x का डिफरेंशिएशन फर्स्ट हुआ cos x, फिर cos x का हो गया sin x विद माइनस साइन. सो ये मॉड ऑफ माइनस sin x, तो ये f डबल डैश x की वैल्यू हुई. x0 हमारे पास है 0.1, 1 है 0.2. सो x lies between this and maximum of this. So maximum of this will be sin 0.2. sin बिटवीन 0.1 और 0.2 के बीच में जो साइन की वैल्यू है 0.2 पर मैक्सिमम होगी, जो की वैल्यू ये वैल्यू आई. सो वी नाउ सब्स्टिट्यूट दिस वैल्यू m2 वैल्यू इन mod even formula in this formula. So we get 1/8, x1 है 0.2, x0 है 0.1 होल स्क्वायर और ये m2 की वैल्यू है. तो ये आपका एरर बाउंड की वैल्यू आ गई. This is another example where we have to find out the polynomial. This is based on Lagrange interpolation because data is not evenly spaced. अगर आप क्वेश्चन देखें that f0 is 1, f1 is 355. So the data is not evenly spaced. Find the unique polynomial of degree 2 or less which fits the given data. तो ये हमने Lagrange polynomial में डेटा जो है this is x0, x1, this is f0, f1 and f2. ये सब इसे सिंप्लीफाई किया, so this is equal to this and finally we get the polynomial 8 square minus 6 plus 1. So this is p2x. अब हमें बाउंड ऑन द एरर फाइंड करना है, तो बिकॉज 3 पॉइंट्स है, so e2 mod is less than equal to 1/n plus 1 factorial means 2 plus 1 factorial, that is maximum of product of this x minus x0, x minus x1 into x minus x2. So x0 is 0, x1 is 1 and x2 is 3. These values you will substitute and x lies between 0 and m3 is maximum of second derivative of function and mod of this x lies between 0 to 3. So we find out maximum of product of these three values. So we multiply them and then first derivative we find out first derivative, put it as 0. So 0 के बराबर रखा, 2 पॉइंट्स वैल्यूज मिली हमें x की, जो कि 2 पॉइंट्स या x की जो 2 वैल्यूज हैं वो ये वैल्यूज हैं 2.2152 एंड 0.4514. इन पर फंक्शन की वैल्यू निकाली, मॉड दिया उसका क्योंकि ये नेगेटिव वैल्यू है एंड दूसरी वैल्यू ये, तो इनमें ये वैल्यू हायर है, बिगर है. सो द वैल्यू ऑफ दिस मैक्सिमम x into x minus 1, x minus 3 where x lies between 0 to 3 is 2.1126. तो ये वैल्यू हमने सब्स्टिट्यूट कर दी. तो e2 mod is less than 1/6, 2.1126 m3. So this is our bound on the error.